This is video number 5, the chapter Refraction. And to start off, I just want to add something to the last bit of the last tutorial. When your angle of deviation is at delta min, what you see is that the angle of incidence is equal to the angle of emergence. Our diagram that we drew was actually at delta min. What you also see is that the angle of refraction 1, R1 equal to R2, which we saw they were both equal to A by 2. So that whole diagram was drawn taking into account delta min. And the most important point, I think, is that say this is your prism here. One second. This is your prism over here. If you're at delta min, your refracted ray inside the prism will go parallel. It'll go exactly parallel to the base. So that's one important property, and I think that there are a few more given in your book. You could go through them. Now I'm going to move on to real and apparent depth. I think it's a relatively easier concept, and I think you all will probably get it. But so I'm just going to go over it very, very quickly, just the basics of it. You have a tub of water or a pool or whatever. You have an object placed at the bottom. This is reflecting light. So we're going to take two rays to draw a ray diagram. This is your first ray. The angle it makes over here is 90 degrees. So as we've already learnt, it will go undeviated. This is water. I didn't write this, sorry. Water, and above it's air. So despite the change of medium, it's going to go straight up. Now it's also going to emit a ray like this. Not emit, but reflect a ray like this. If you draw the normal, it's going to come out to be something like that. And since it's going from denser to rarer, water to air, the ray is going to go away from the normal. So something like this. Drawing the arrows. Now, if you're standing here and watching this, you'll actually retrace the path of this ray over here. You'll look at it, where's it coming from? And if you trace its path backwards, you're going to see it's coming from somewhere here. Whereas originally it was coming from here. This is what the whole concept of apparent depth is about. You actually, if you're standing over here, you'll actually see this light coming from an object over here. And hence you'll feel that it is shallower than it is. You can see that the height of the actual object is much lower. It's much deeper than that of what you'll see. But this is all caused due to refraction. If there was no refraction at this surface here, this would have gone straight and there would have been nothing there. It's only because light bends when it leaves the water. That's why your eyes just trace the path backwards and find this point here. And that's why they think the object is placed. So I think you guys would have already understood the concept, but this just to go over it. And there's a formula. Real depth. Real means where it is actually placed. Real depth upon apparent depth. Apparent is where your eyes imagine it to be or where your eyes see it. Apparent depth. This is mu. You can write RD over here. What this basically is refractive index of the medium that you're using at the bottom where the object is placed. So in this case it's water. So what you'll see is that for example, water's refractive index is nearly, you can take this 4 by 3. So say you've placed an object at say 5 meters, and that'll be the real depth, so 5, and you want to find the apparent depth, so write AD over here, cross multiply, and you get that 4 AD equal to 15, so that will be 15 by 4, which will come out to be 3.75. So you can see that what your eyes will look at it as, it'll be 3.75 meters deep according to your eyes, but whereas actually 5 meters. It's due to the refractive index of the material that you use. And similarly, if your refractive index is much more, say you have glass instead, then the effect will also increase. So now the next topic is critical angle, but before I move on, I need to make space. Okay. So critical angle, the definition, if you read it, is it's an angle for any given pair of media. It's the angle of incidence in the denser medium such that the corresponding angle of refraction in the rarer medium is 90 degrees, and its symbol is C. So critical angle, I think you'll understand definition better when I actually do it right now. Say you have this is your glass slab as usual. You have a ray coming here, normal. I'm choosing a different color now. And say your ray goes like this. It goes parallel to the block, the side of this slab. So you can see here that the angle of incidence is this. The angle of refraction is 90. Angle of refraction is 90. Whenever we're talking about critical angle, we're talking from denser to rarer, always. We're just finding the critical angle of the glass slab such that when you incident a ray at that angle, your angle of refraction will be 90. That's all it is. And when your light is going from denser to rarer, if you just apply Snell's law over here, you'll get sine I upon sine R. Now, your I is actually your critical angle, so you can write sine C, and R here, remember, is 90 degrees, and sine 90 is 1, so we can just write sine C over here. But this is mu of R with respect to D. If you want the opposite, if you just apply a principle of reversibility of light, what you will get is that mu of D with respect to R is equal to 1 by sin C. This is the only formula you need to know over here, and I think the concept is much better explained in the textbook, very detailed also. So I guess if you haven't understood from here, you should look at it over there. But I don't think you should have any problems in understanding really. The next topic and the last topic in the chapter is called total internal reflection, denoted by TIR over here. So it's just a phenomena due to which a ray of light that's traveling from optically denser medium to optically rarer medium gets reflected back into the denser medium at the surface between the two. All we're saying is that if you have a glass slab like this, you have a ray of light that's coming from, say, here. It comes over here and it just reflects back. Usually what you'd see is that it gets refracted out like this, but in total internal reflection, what we're saying is that it just bounces back into the denser medium. Remember, this is denser, this is rarer, right? So in total internal reflection, the condition for it is that the first most important condition is that it needs to be from denser to rarer, otherwise there will be no total internal reflection. The second one is that the angle of incidence, if you look over here, this angle of incidence must be greater, angle of incidence must be greater than the critical critical angle for these two this pair of media, because just look at it this way. If you have a slab like this, I'm taking an incident ray at a very small angle first. Now this is definitely lesser the than the critical angle for these two. I'm taking glass and air over here. For glass and air, I think it's 42 degrees or something. But what'll happen is that it'll just get refracted out. If I take a ray that is equal to the critical angle, you know that it's going to just have a 90-degree angle of refraction. But now if I take something greater, where the angle of incidence is greater, you can see it's going to get reflected back like this. And then maybe when it hits the second surface, it's going to go further out like this. That depends on the other angle. But just understand that this angle of incidence needs to be greater than the critical angle. Otherwise, refraction will take place. So these are the two necessary conditions. Now in your book, uh, they've given loads of examples of prisms and various diagrams, various types of prisms, total internal reflection. That part of the chapter is very important. The uses of all the prisms very important, and I'm not doing it because number one, I don't see the point in doing it. I can only just draw the diagrams again and trace the path of light, which I think is done in the book as well. And secondly, it's I don't think it's very tough. You just need to follow the diagrams and follow these two rules over here. Denser to rarer, and angle of incidence must be more than the critical angle. And your basic rules of reflection, that your angle of incidence is equal to your angle of reflection. That's it. And the uses, I mean, if you understand how it works, you'll understand the uses as well on your own. So unfortunately, I can't teach you anything over there, and I'm going to have to leave this chapter over here. If, of course, you have a doubt or problem over there, tell us and we'll figure out a way to help you. But in this tutorial, I'm going to leave it over here. So thanks for watching, and next time we'll be covering lenses.